recording. Wonderful.
This meeting is being recorded.
Thank you all once again for joining us. I believe everybody here today is the same as last week, but nevertheless, let's introduce Alexander once more. So Alexander Rothkopf is a professor of physics at the University of Stavanger in Norway. Professor Rothkopf received his PhD in physics from the University of Tokyo with a research area in theoretical high-energy nuclear physics with a focus on real-time dynamics from Lattice Qcd. And in particular, Alexander is truly a world expert in heavy quarkonium and its modification in nuclear media, especially from the perspective of Lattice Qcd. So we're very, very thankful that you took the time to come talk to us last week as well as this week, and in particular for this week, where we will talk about your area of expertise. So if people, as in last week, have questions, please shoot them out as we go along. Otherwise, we'll have questions at the end. And Alexander, please take it away.
Thanks, Will. Thanks, Phys.Rept. It's great to be back after 1 week and to have a chance to now tell you in a bit more detail on what I am or have been working on for quite some time now. And so indeed, today I will be focusing on the bound states of heavy quarks and antiquarks, heavy quarkonium in a medium, and going from the complex potential to the Lindblad equation. And so I will start out with a physics motivation that connects to heavy ion collisions. Then I would like to tell you about our work on describing heavy quarkonium dynamics through a potential picture and how to extract that potential from Lattice Qcd. And then I hope time will permit to now connect this to the open quantum systems description that I mentioned last week, where we now describe heavy quarkonium evolution as an open quantum system using as input this heavy quark potential. Okay, so let's start with the physics motivation. And here we are at CERN, the Large Hadron Collider, which allows us to collide lead atoms under relativistic energies at one of the 4 experiments. And what is happening is that you have your 2 projectiles, you crash them into each other, and in the overlap region that is determined by your that is determined by the centrality of the collision, you have now a you condense an enormous amount of energy in a small space-time volume, and we are trying to. The community is trying to better understand since 20 years what is going on in the inside of this collision, and essentially the following very rough picture has emerged. So if you think about now looking into the beam direction, you have these 2 overlapping projectiles, and then as they hit, the 2 projectiles hit, the partons inside start to see each other. You will generate color flux tubes between the quarks in the projectiles, and that leads to very strong coherent color electric and color magnetic field that we call the Glasma stage. And if you pull now these color strings strong enough or far enough, they will rupture and pop out quarks and gluons out of the vacuum, which efficiently exchange energy and momentum to eventually form a locally thermal collection of deconfined quarks and gluons that we then refer to as the quark-gluon plasma. This state expands and cools over time of around 5 to 10 Fermi until it hits the hadronization temperature of around 155 MeV, where now those colored quarks and gluons come together in color neutral mesons and baryons that then propagate into the detector and get measured by experiment. And now, obviously, we would like to better understand, for example, this quark-gluon plasma phase of the heavy ion collision. And there are multiple different probes that you can use. And in this talk, I would like to focus on one specific probe, which are heavy quarkonia, the bound states of a heavy quark and antiquark. The importance here is that these probes are really unique because these are probes that are both susceptible to the quark-gluon plasma in which they evolve, but they are also distinguishable because they contain an intrinsic large scale. So they are the bound states of a heavy quark and antiquark. And in vacuum, already these are really interesting states. They only decay into 3 gluons due to the OZI rule. Many hadronic decay channels are actually prohibited, and that means you will find a kilo electron volt width. There's a lot of, so in keV, that's tiny compared to the MeV scales you would expect usually for a hadron. There's then therefore a significant decay into dileptons, electrons and muons, which make for very clear signals in experiment. And for us theorists, what is interesting is that these bound states are non-relativistic because the heavy quark rest mass is both smaller than the intrinsic scale of quantum fluctuation in QCD, lambda QCD, and actually also larger than the binding energy of that state. And usually these quarkonium particles, because they are non-relativistic, are classified according to the scheme you know from atomic and molecular physics. So you have your 2s plus 1 up, L angular momentum, so spin up, angular momentum and total spin scheme. And so the heaviest, so the most deeply bound state is the epsilon ground state, vector channel ground state. This is a 3s1 state. Then you have the chi-b state. So this is the epsilon is a BB bar state, bottomonium, with no intrinsic orbital angular momentum. The chi-b is a BB bar state with that has intrinsic angular momentum, so it becomes a p wave state, and then you have the next less deeply bound state is the J psi, that's a CC bar state, and so you'll find a whole zoo of these states that you can, for example, order according to the binding energies. And now in a heavy ion collision, the life of a heavy quarkonium particle evolves concurrent to what else is happening in the heavy ion collision. And so essentially in the earliest stages where there's still enough kinetic energy, or essentially kinetic energy to the partons, the partons can actually create these heavy Q and Q bar pairs. And these, after radiating off some of the color that they usually possess, they can form a color neutral QQ bar state. And this quarkonium state now evolves in the environment made up by the quark-gluon plasma. It interacts with this hot environment, and you can ask, for example, does it survive this evolution, or does it eventually melt into its quark antiquark constituents? And once you reach the hadronization stage, then you can either have that a surviving in medium state transitions now into a vacuum state, or what we now know from LHC, for example, if you create a lot of CC bar pairs in the beginning, then there's a non-negligible chance that even if they are all the quarkonium has melted, at hadronization, a CC bar pair can come together again and form a vacuum state, and by that replenish the yields of the charmonium. Okay, that being said, well, our friends in experiments, they have accumulated a wealth of data. Let me just show you two, say, iconic plots here. One is from the CMS collaboration, and that shows the comparison between the PP collision I-muon spectra for bottomonium, that's the red dashed curve, and the corresponding data in a heavy ion collision, that's the blue curve. And what you can see is that if you normalize this to the same amplitude for the ground state, you can see that in a heavy ion collision, the excited states seem to be much suppressed. And we interpret this as the bottomonium actually plowing through that quark-gluon plasma as a non-equilibrium probe of the full QGP evolution and getting kicked on its way and getting destabilized as it moves. And at the same time, for charmonium, so charmonium is much lighter, and therefore one expects that it actually has a chance of kinetically equilibrating with the surroundings, which is supported by findings by the Alice collaboration that that heavy quarks seem to have, and even quarkonium seems to have a finite V2, so they participate in the collective behavior of the bulk, and so these are indications that there's at least partial kinetic equilibration, and therefore of the charmonium. And once you have equilibration, that means you will have a loss of information on the initial conditions, and that means that charmonium is potentially a probe more of the late stages of the collision. And of course, the goal for theory then would be to provide a first principles interpretation to all of this intricate phenomenology. Well, we are if we want to do so, we have to deal with a system that is strongly coupled. The quark-gluon plasma created in a heavy ion collision is in a temperature range that is very close to the pseudocritical transition temperature, where weak coupling perturbation theory methods that work well for high energy particle physics experiments, where these techniques don't work anymore, and so we have to use other tools, and one robust tool is Lattice Qcd, and it's essentially one of the very few non-perturbative first principles approaches to the theory of the strong interactions, to quantum chromodynamics, and where you now discretize space-time into a hypercubic grid. The gauge fields A that you know from your textbooks, they now live on the grid links connecting individual nodes. The fermions are positioned on the nodes, and the important technical aspect here is that you're not formulating this in Minkowski time, but you're formulating these Lattice Qcd setups in a artificial imaginary time that is related to the inverse temperature of the system. What you then try to do is you try to compute the quantum expectation values using Feynman's path integral as a path integral over the links, for example. And in practice, what you do is in Lattice Qcd, you write down a stochastic process that generates an ensemble of different gauge configurations that is distributed according to the Feynman weight e to the minus s. And you generate these configurations, you compute the observable of interest on each of these configurations, then you take the mean, and that systematically approximates the quantum statistical expectation value of interest. Lattice Qcd has been really an important tool to investigate the static properties of QCD, so thermodynamic properties, for example, to establish the pseudocritical temperature and to explore the equation of state. This is one of these successful collaborations in the lattice community, where you have here you see, for example, the pressure of QCD. This is the red curve, and you see actually a colored curve and a gray curve, and these are the continuum extrapolated. So the final results from two major collaborations that, while they use different discretizations, as they extrapolate to zero discretizations, they end up with the same results, giving you a trustworthy result on, for example, the pressure of QCD, and also really non-perturbative objects like the trace anomaly around the transition temperature. So Lattice Qcd is an important tool, and we are going to use it. And so what we're after is we want to understand heavy quarkonium in a thermal medium. And in the rest of this talk, I will try to look at two different. I will go into two different foci. The first one is to really understand heavy quarkonium in thermal equilibrium, meaning that here we are not interested in time dependence, but the guiding principle will be the separation of energy scales. What we're going to do is we're going to use so-called effective field theories to derive quantities that help us understand quarkonium in thermal equilibrium. And the goal here will be to define and extract the time-independent potential acting between these heavy QQ bar pairs from lattice QCD. And the technical aspect here will be that we're going to use so-called in-medium spectral functions. And I'll get into more details what these are. And then, if time permits, I hope that we'll be able to discuss non-equilibrium dynamics of heavy quarkonium, where now the guiding principle is the separation of time scales. Obviously, energy scale and time scale separation are, of course, related. We will talk about heavy quarkonium in terms of an open quantum system and its master equation for the density matrix. And I will tell you a bit about how we try to describe the evolution of heavy quarkonium using so-called quantum state diffusion, where the technical goal is to compute so-called survival probabilities that tell us how much of a initial admixture of quarkonium has survived over time. And while thermal equilibrium studies can be done in lattice QCD fully non-perturbatively, the non-equilibrium description so far has not been established fully non-perturbatively. Okay, let's start with thermal equilibrium and the quest to explore whether a potential description for the physics of heavy quarkonium is actually feasible. Okay, so of course, if the starting point of everything is QCD, that is a field theory where the interaction between the quark and antiquark is described by gluons, and there's nowhere a potential to be found. However, we already know that there exists a separation of energy scales between the intrinsic scale of QCD, lambda QCD, and the heavy quark mass, and also the temperature for a system and the heavy quark mass. And when you have such kind of scale separations, you can actually simplify the language you use to describe your heavy quarks, because that simply means that neither the temperature fluctuations nor the quantum fluctuations can actually create spontaneously a heavy QQ bar pair. And that means we can go over to a non-relativistic language to describe heavy quarkonium. And the way to do that systematically is by using the concept of a effective field theory. You also start off with QCD, where the heavy quark and antiquark are Dirac fields. Then you decouple the upper and lower components, so to say, of your Dirac spinor into two-component Pauli fields. And you've all done this when you derived the Schrödinger equation from the Dirac equation in the quantum field theory class. And then you get a field theory of these non-relativistic spinor fields. And if you then exploit further this separation of scales, you can actually go over, and so this Pauli field theory is called non-relativistic QCD. And if you then exploit further this scale separation, you can actually leave the language of fields altogether and go over into a language of non-relativistic wave functions for your heavy quarkonium system, where you talk about color singlet and color octet wave functions. So your quark and antiquark is charged with a color charge that is triple valued. And so you can combine these group theoretically in either a color neutral configuration, that's the color singlet, or into 8 different color octet states. And the question is then, how do these wave functions evolve? And what you can show is that in PNRQCD, the time evolution of the correlator of such wave functions is governed by a non-relativistic potential term that we would call the heavy quark potential plus systematic corrections in terms of the in higher powers of the inverse heavy quark mass, and then a potentially, no pun intended, a term that is that describes possible non-potential effects that can arise from the original field theory nature of the interactions. So what you now can do is you can try and, whenever you try to set up a effective field theory, you define the relevant degrees of freedom, in our case here the color singlet and color octet wave functions, and you write down the most general Lagrangian for it, and this will have certain parameters in it, so-called Wilson coefficients. And in order to connect your effective field theory to the underlying field theory of QCD, the microscopic theory, what you have to do is you have to carry out what is called matching. And the matching is such that you're essentially calibrating the parameters of your effective field theory such that it reproduces the correlation functions of your microscopic theory. And for that, you have to identify observables in both the microscopic underlying theory, QCD, and in your effective field theory that have the same physics content, which you can then require to give you the same physics in both the microscopic theory and the effective theory. And from this requirement, you can then tune the parameters of your effective field theory. And in PNR QCD, what you can show is that the correlation function of the singlet of the color singlet wave functions at unequal times can be related to a well-known QCD quantity, and that is the so-called Wilson loop. So what's going on here? If you think about, you have a heavy QQ bar pair described by a singlet wave function at time 0, and then you want to understand how it has evolved until time t, then the microscopic counterpart to that is that you put in QQ bar operators at t equals 0, and you have the destruction operators for QQ bar at time t. And if you make the mass of these heavier and heavier, then eventually the correlation function in QCD that describes this propagation turns out to be this so-called Wilson loop. And this Wilson loop is a purely gluonic object. It's an object where you take the exponential over the gauge field as it along this rectangular path that this static Q and Q bar pair now traces out in time as it evolves. And indeed, if the Wilson loop can be related to this correlation function of singlet operators, then surely we can now relate, for example, this potential term up here to the behavior of the Wilson loop. And so if the singlet correlator obeys the Schrödinger-like equation, so will the Wilson loop. And we can take this and turn it around into a definition, therefore, of what we mean by this potential. So if a potential picture is valid, meaning this theta term here is small and this O is also small, then you would have I dt times this correlator equals a time-independent potential times the correlator itself. So now we identify this correlator with the Wilson loop. And so if I now want to write what is V, and I take the time derivative of the Wilson loop divided by the Wilson loop, and then define that this is the potential. Why do I write a t to infinity here? Well, as I said, the microscopic theory is a field theory. There is no potential. And if you want to replace the interaction mediated by gluons by an instantaneous potential, you will need to do some sort of a time course graining. The gluons must have hopped between the quark and antiquark several times before you can replace the interaction by a potential. And so this is why one then formally always looks at this ratio at very late real times. And what was very interesting is that when people the first time evaluated this quantity, in perturbation theory just to see what would come out at high temperatures. Then they found that, well, since the Wilson loop is in real time is complex, this whole thing could be complex. And that was a rather surprising fact at the time, so that we will have to deal with a complex valued potential. So how do we, once we have defined the potential from arguments related to effective field theories, now the question is, how do we get our hands onto it? And I would like you to remember that everything we did here happened in real time. This is, the T here is Minkowski time. But then on the other hand, I told you that lattice QCD simulations do not take place in Minkowski time, but due to technical reasons are formulated in imaginary time. And so how can we bridge this? And this is where the concept of a spectral function comes in very handy. And it comes down to the fact that correlation functions in a quantum field theory can usually be written by what is called a spectral decomposition. So for example, for the Wilson loop, you can show that the real-time Wilson loop can be written as a Fourier transform over a positive definite function rho, where all the time dependence is here in this integral kernel. And now you can see where this game is going. If I go from real time to imaginary time, the only thing that changes is the integral kernel, but not the spectral function. So we can simulate the Euclidean time Wilson loop. And if it was possible to extract from it the spectral function, then that would give us information already about the real-time Wilson loop. Okay, so if we have this spectral decomposition, we can use it and plug it into our definition of the QCD potential, and that allows us to relate the potential directly to the spectral function of the Wilson loop. That is a rather cumbersome expression here. So maybe we can actually do better, and maybe we can actually find out whether we could use this formula here to figure out what structures inside the spectral function actually encode the potential. And this is some work that I did a few years ago with Yannis Bernier, where we looked at if the potential picture is valid. That means if the Wilson loop becomes at late times can be described essentially by a single sine cosine contribution, then its spectral function will exhibit a specific behavior. Namely, first note that there's this t to infinity limit in front of something that contains a Fourier transform. Large times in a Fourier transform means small frequencies. So the physics of the potential must be encoded in low-lying spectral structures. And indeed, what we could show is that if the potential picture is valid, then the Wilson loop will contain a well-defined Breit-Wigner, skewed Breit-Wigner-like peak, the position of which encodes the real part of the potential and the width of which contains describes the imaginary part of the potential. So by this, we could relate structures inside of the spectral function directly to the values of the potential. Okay, well, that means we have to get our hands onto those spectral functions, and that is a tricky business. And I will go much more into, in more details in this. But here's just as a preview that there are different methods on the market how to do that. And this is one of the main technical aspects that I've been working on, how to extract spectral functions from Euclidean correlators that you simulate in Lattice Qcd. Okay, what is it that we actually have to do? I told you we can simulate the Euclidean correlation function, and it is related to the spectral function via an integral transform. And actually, for our case, it is related via this e to the minus omega tau term here. And if you look at this, this looks very much like a Laplace transform. And what we want is we want to get our hands on the row. That means we would have to invert this Laplace transform, and inverting the Laplace transform is the canonical example of a ill-posed inverse problem. If you discretize this, so you have a certain number of simulation data inputs, and now you discretize your spectral function over, say, n omega frequency bins, then you get this type of relation where you're now trying to find a set of rho L parameters that would reproduce your simulation data di. Obviously, we have many more parameters usually than we have data points. And these data points, it's a Monte Carlo simulation, Lattice Qcd, meaning the data comes with a finite precision. And so there exists an infinite number of rho Ls that all reproduce your simulation data within the error bars. And the question now is, can we still make sense out of this? And yes, I would like to answer with a resounding yes, but that means we need to find additional information we have about the spectral function to arrive at a unique answer. And for this, I've been working with Bayesian Inference, which is a data analysis technique that relies on Bayes' theorem in the following form. Bayes' theorem tells us that the probability of some test function that you can pull out of a hat, the probability for that test function to be the correct spectral function given your simulation data and any prior information you have on the spectrum is proportional to two terms. The first term is the so-called likelihood probability. That's the probability of the data given your test function. And this is nothing but your chi-square fitting probability. The chi-square fitting functional is hiding in here. How well does your essentially does the test spectral function agree with the measured data? But then Bayesian inference tells you that there should be a second term, namely a regulator term that's called the prior probability, which tells you how compatible your test function is with your prior information. And so, for example, in Lattice Qcd, we often can rely on the fact that the spectral function should be positive definite. And so positivity would be one of these additional prior knowledge that we have that we can include in this Bayesian approach here. Once you know what your likelihood function is and what your prior is, you would then go ahead and look for the most probable spectral function rho given your simulation data and prior information, meaning you would look for the maximum of this term here on the left that is called the posterior. In the literature, if you go and look to papers doing this business, you often find people talking about a default model and hyperparameter alpha. And just to give you what they mean is that your prior probability is often, it's a probability distribution, and you can, so it has a certain shape, but then usually you fix its maximum. That is what the default model does. And then you have this distribution has a certain width, and that essentially encodes how confident you are about your prior information. And this is usually encoded in the confidence, so-called confidence parameter alpha, just to tell you a bit about the vocabulary in this business. And the prior information now comes in both by the choice of your prior functional, and I write this here as S because one usually parameterizes this prior probability as some e to the S. So the functional form of your prior probability and the values you choose for the maximum of that distribution. Okay, so in the literature, on the market, there are several different of these regulator terms. The oldest one that you've seen probably is Stikunov regularization, which in the Bayesian language is nothing but a Gaussian, amounts to a Gaussian prior probability. So it's just rho minus m squared that you get in this regulator. And so also if you're looking at more modern machine learning based approaches to spectral function reconstruction, you will often see that in the end, it turns out to be some variant of Stikunov regularization that shows up. Here, for example, Stikunov does not take into account the positivity of the spectral function. So any type of rho, either positive or negative, is admissible. You might. Is there a question? Okay. If there is, there's another method on the market that you might have heard. That's the so-called maximum entropy method. That uses this particular regularization term. It's the so-called Shannon-James entropy. And you can see that here, this now has a term that contains a log rho. And so this regulator apparently knows about positivity and prevents the rho from actually taking on negative values. So in this implementation of the Bayesian approach, positivity is baked in. And I don't want to go into the details about the MEM at this point. I would like to rather tell you about a more recent method that I'm very happy to have contributed to by deriving this or by constructing this specific regulator term, the BR method. It also enforces positivity, and it is derived from a smoothness and so-called scale invariance axiom. Essentially, we wanted to make sure that the choice of units does not affect the end result of our regularization. That's why there's only ratios of rho and m showing up, while the MEM, you actually have to worry a bit about what's the influence of units there. And this BR regulator turns out to be essentially the one with the weakest curvature of all the regulators on the market. So it will allow you to regularize the inverse problem, so you get a unique answer, but it does so in the weakest form possible, allowing your the influence of the data in your likelihood to express itself most freely. Now, you can say, well, there are some assumptions going into the choice of this regulator, and that's true. However, you can always be sure that in the what I would call the Bayesian continuum limit, all of those converge to the same correct result as you make the number of data points go to infinity and the errors on the data go to 0. And the choice of S influences how efficiently and with what kind of artifacts you are converging to that limit. Okay, let's go back to the physics goal. We want to extract the heavy quark potential. So we're going to compute the Wilson loop along Euclidean time. This is what we can do from Lattice Qcd simulations at different spatial separation distances of this static quark pair. And then we have to compute the spectral function for each of those Wilson loops. We are going to look whether there exists a well-defined lowest lying peak. And if it does, it signals to us that a potential description of this quark-antiquark or the static quark-antiquark pair is possible. And from the position and width, we can read off the real and imaginary part of the potential. Just to give you, to be clear up front, while I've been talking about the Wilson loop here up to now, the Wilson loop actually in practice is a quite difficult object to simulate or to handle, because it has 90-degree corners, which introduce a class of divergences called cusp divergences. And in order to avoid those, we are actually going to use Wilson line correlators, where you have removed the spatial connectors of the Wilson loop in fixed to Coulomb gauge. Okay, so I show you this picture. Do we have a chance? That could be a theorist's dream, and it could be completely infeasible in practice. So let's try it out with a test case where here I show you some hard thermal loop perturbation theory spectral functions that you can compute analytically. You can then compute the corresponding Euclidean correlator, discretize it, and throw some noise on it and feed it to your reconstruction method of choice. If we do this with 12 data points, which is really a tough test case because this is really few points that we have available, and we don't have percent level errors, then you can see these blue curves. So there's gray curves here. That would be the, sorry that this doesn't come out very nicely. So you have the gray curves, which is the hot thermal loop spectrum that you want to reproduce. And then what you see is with the blue curves, that's for 10 to the minus 2 errors, you get the position somewhat okay-ish, but the width is overestimated. And then as you make the errors smaller, you see that for the intermediate distance results here, around the peak tip, you're really very well reproducing already the results. Here, I would like to mention that one of the yes, Daniel?
Yeah, hi, if you could go back. So I remember earlier talking about the, sorry, next slide. You're talking about that
This one?
No, sorry, like 2 or 3 slides forward. No, forward.
Forward.
I think slide 13 or 14. Yes, this one. So
Yes.
you're talking that the potential, you can read off the parts of the real part and the complex part by looking
Yes.
at the width and position of these peaks. I see it looks like this method here will preserve the positions of the peaks but muddles the width. So does that mean that using this method you can precisely extract real bits but just not imaginary, or is there an extra step?
You can so since you will be able to reproduce the spectrum exactly in the Bayesian continuum limit, the question is how good are you, how well are you able to reproduce certain properties of the spectral function? And what you find in general is that the location of a peak is much easier to reconstruct than the width, because there's much more ambiguity possible for the width of a peak given some Euclidean data than for the position of that peak. So this would be the next slide, the next step indeed. Here on the right, on the left, I show you the expected values for the real part of the potential in gray, and then you can see how the reconstruction does for 10 to the minus 2 and 10 to the minus 3 errors. And you can see that one is doing not too badly to reconstruct the real part, but you can see on the right, where it's about the imaginary part, with 12 data points, there's no way to do this right. However, if you increase the number of data points, you have a better and better chance of getting closer and closer to this gray curve here. And then you have to understand, if you now do this extraction on real Lattice Qcd data, you will have to figure out how close you are already to the correct solution and make an estimate of your systematic uncertainties.
All right. Yeah. Okay. Thank you.
Sure. What I since I worked on constructing this BR method, I would like to point out that the BR method is really essential to get the potential extraction right, because it was the only method that we found that allows us to reproduce the Breit-Wigner-like shape of this in these spectral functions, while the other method on the market, the maximum entropy method, always gave you Gaussian-like structures, where then the fitting with the correct spectral shape would give you values that does not allow you to reproduce the real part in the same accuracy. Okay, so I should show you actual data here. Was a study from a few years ago in quenched QCD. And just to show you here, what we do is we simulate the system at the same lattice spacing, but we change the number of points in the temporal direction. And if you change the extent in temporal direction, that means you're changing the temperature. And so we did the analysis of the Wilson line correlators and Coulomb gauge here at high temperatures. That's the spectral functions on the left. So you see many different spectral functions corresponding to Wilson loops with different spatial separation distances. But what you can see is that all of them show one dominant lowest lying peak and then some shoulder structure. And that means you can identify a lowest lying peak that will translate into a heavy quark potential. And here on the lower temperature configurations to the left, you also see you get a well-defined peak, but you see also that they somehow they seem to behave differently. The peak positions as you increase the spatial separation distance. So we have our spectral functions. We can fit the peak position, and this gives us these results for the real part. Here I have by hand shifted them in the y direction to better be able to compare them. Below TC in the confined phase, you see that the potential doesn't care for temperature because there's only glue balls available to scatter with the quarkonium. Glue balls are very heavy, so this is very unlikely to happen or unlikely to have a major effect. And then in the deconfined phase, it appears that the potential changes significantly and eventually actually flattens off as you go to higher and higher temperature. And this flattening off is something that one knows from, or one can make a connection to abelian plasmas, where one knows the phenomenon of Debye screening. When you have light charge carriers, they will screen the charges of external sources. And usually you describe the screening by a screening mass. So you can extract the screening mass from this by doing fits, that's the solid lines. And so below TC, there's essentially zero screening mass. And then as you go into the deconfined phase, we find a larger and larger values for this screening mass. We also try to look for an imaginary part in the potential. Again, this is much less robust because we are dealing here with the width. But we seem to be able to find a indication for the finite value of the imaginary part on the lattice. And mind you, here we have 20 to 72 data points available, so much more than the 12 data points that we did the test for. Okay, so this is quenched QCD. Then we wanted to eventually go towards the full QCD potential. And so we did a first study, again, a few years ago, using a legacy discretization of full QCD, the so-called ASTAT action. Again, we scanned a few temperatures. And here, what we found for the real part was that, again, you get this Coulombic and linearly rising behavior of your real part at low temperatures. And then in contrast to quenched QCD, where you had nothing happening below TC, and then you had this sizable change in the deconfined phase here, because now in full QCD, there's no phase transition, but a crossover. It seems that this potential is gradually weakening as you increase the temperature, which would be consistent with intuition. Again, we also try to extract an imaginary part, but here we really only have 12 data points available on each lattice, and this is why we suggested a consumption of a lot of sodium chloride with those results. And so the current work is to extract the potential on realistic modern lattices, and to just show you what kind of challenges we are now dealing with is that as you want to do better and better lattice simulations, you want to go closer to the continuum limit. And for this, it has been vital to introduce so-called improved actions. These are more intricate discretizations of the QCD Lagrangian, and these improved actions have been vital in the exploration, for example, of the thermodynamic properties of QCD, the equation of state. However, when you're now trying to do spectral analysis, one finds that there's a competing interest here, because your improved actions actually introduce artifacts that your spectral functions are not positive definite anymore. And you can imagine that this is a pretty big bummer. One example here, let me not go into detail. If the spectral function of this quantity that I show you here would be positive definite, it should monotonously decrease from larger values to smaller values and then eventually plateau off. But you can see that there's a non-monotonicity happening here, and that tells you that there are non-positive definite contributions in the underlying spectral function. And all of the MEM and the BR method that I told you before about, they all relied on positivity. And so this is a big throwback that in this high precision data, or these modern data sets, we cannot use these methods. And so we need reconstruction methods that actually work on non-positive definite spectral functions. And so recently we've now worked out a new method, so-called PADE projection method. It's a non-Bayesian reconstruction method, and it works in the following way. So you have your Euclidean correlator. That's when you look into a lattice paper, that's usually how you see correlation functions plotted versus Euclidean time. But you can actually take a discrete Fourier transform and take this from the Euclidean domain into the Matsubara frequency domain, and then you get a real and an imaginary part of this correlator. And what we are going to do is we're going to interpolate these data points with a rational function. That's the whole point of the PADE approximation, that you can write, that you can approximate a function by a rational function. And there actually exists a very nice recipe in the literature, the so-called Schlesinger formula, that allows you, that is an interpolation formula of data points that we generalized to complex valued data points. And so there exists a recursive, it writes the rational approximation that you're looking for in terms of a continued fraction. And then there's a recursive algorithm that allows you to compute the parameters of this rational interpolating function using your data points. And if you do that, well, you get a rational approximation to the Euclidean correlator that depends now on the Matsubara or the imaginary frequencies. You can then by hand do the analytic continuation. That gives you then the retarded real-time correlator. And if you take the imaginary part of that, so you go and look into the textbook, it tells you that the retarded correlator is related to this spectral function, and so by taking the imaginary part of that, you immediately have your hand on the spectral function. And indeed, this is how this specifically looks for this Wilson line correlator data here. And again, you can see that you get a result where you have a lot of these, so you get different spectral function for different Wilson loops of different separation distances. And you can now investigate the peak position and width of this lowest lying peak structure. What is nice about the rational approximation is that you have direct access to the pole structure of your correlator, actually. The drawback here is that because there's no regularization present here in the sense of the Bayesian inference, this method is very sensitive to noise. And so the question is, can it do something with real data? Again, I want to show you some mock tests here. And so we have the hard thermal loop spectral functions for which we can also compute the correlation functions at 12 data points. We throw noise on it. And here is one example. Actually, this is only for 10 to the minus 3. And so you can see the gray spectral function is the spectral function you want to reconstruct. And then the blue ones are the PADE reconstructions here. And if you now look at what you get for the real part and the imaginary part, then again, you find that the PADE is actually able to extract the real part of the potential. And however, it is very much underestimating the imaginary part. So again, it is we seem to have access to the real part, but we will probably be struggling with the imaginary part of the potential. Okay, and so now comes, okay, having seen what the BR method on previous studies gave. Now we take the state-of-the-art Lattice Qcd ensembles from the Hot QCD collaboration, 12 data points in time, but humongous statistics, so really percent or even sub% error bars on the data. We compute with the PADE the spectral functions. We look at the position of the peaks, and we do that at different temperatures. And there is a result, and we just published this, that I must admit I completely do not understand so far, which is that we see that nothing happens in the real part. And so this is extremely puzzling, and we have to wrap our head around this. You can think, okay, maybe the PADE simply didn't work. And I see that I'm almost out of time already. So I wanted to show you two more methods, how we cross-check this. And essentially, the point is that also the other method that we used, these black dots, the black squares here versus the PADE, which is the green, they all line up with the t=0 result and tell us that there seems to be no in medium modification of the real part. So this is very, very confusing, and we'll have to figure out what is going on there. So there's still the question of the real part in full QCD of that potential is not yet clarified. What about the imaginary part? All of the methods we tried tell us that there is a finite imaginary part, but there's still a sizable difference in the values that we get out. Again, let me say the original method that I developed to extract the heavy quark potential that has worked very well on positive definite spectral functions, the BR method, is not applicable to this modern data sets because the improved actions introduce non-positivities, and therefore the next thing that we have to do is we have to use all these methods that we now developed for non-positive definite spectral functions and redo the analysis on quenched QCD data, where the underlying spectral function are purely positive definite, and the BR method is valid, so that we can really figure out whether this new results here on the real part, whether that's a methods issue, whether it's a simulation issue, but this is something that we're currently trying to better understand. Now I see that I'm really out of time, so I unfortunately have not that much time to tell you about heavy quarkonium as open quantum system, but let me try and tell you a bit what we're trying to do here. Essentially, I would now have repeated what I talked about on Friday. Let me skip this. This is the introduction for the heavy quarkonium for the open quantum systems. The most important result here is that the evolution of the quarkonium can be written as a master equation for its density matrix, which follows this type of Lindblad equation. Now, the question is, how do you get the Lindblad equation? And you can derive it from the path integral. I will again not go into the details. The point is that even though you're talking about non-relativistic heavy quarks in a language that looks very much like quantum mechanics, the derivation of this language proceeds from the relativistic path integral, where you're essentially explicitly integrating out the medium degrees of freedom. So technical steps. The point is, you can write the spectral function of the QQ bar system as a path integral that only is formulated in terms of, and here the x and y would now be the quantum mechanical paths of your quark and antiquark, where you have a since you're since this is a mixed state, you're what is called on the Schwinger-Keldysh contour. I'm just going to be very brief here. So you have two actions here, one for the so-called forward propagating and one for the backward propagating path. The important point is that the effects of your heavy quark system that couples to the medium can be encoded in one explicit term in your path integral, and that is the so-called Feynman-Vernon influence functional. This in general is a very complicated function, but given the separation of energy scales and the corresponding separation of time scales between the medium and the heavy quarkonium, you can actually approximate this by simpler functions. And what I wanted to show you here in this section is that there's three contributions to this Feynman-Vernon influence functional. There is a potential, there's this one part that is related to the coherent dynamics of the Lindblad equation. Then there is a fluctuating part that is related to energy being pumped from the medium into the QQ bar system. And then there is a dissipative part that is related to the quarkonium shedding energy back to the medium. And both fluctuation and dissipations depend on the imaginary part of the potential I discussed in length before. And you can then go on and derive the Lindblad equation. I showed this to you before, and you can now identify which parts of the influence functional show up in your Lindblad operators. Where do the fluctuations, the physics of fluctuation sit? Where does the physics of dissipation sit? And since I am out of time, let me briefly jump over this. Here, I wanted to show you that what phenomenology has been doing over the past, let's say, for the past 15 years or 20 years, was essentially trying to solve a deterministic Schrödinger equation for heavy quarkonium. What we could show is that once you have the full Lindblad equation, you can show what kind of additional approximations you would have to assume so that everything reduces to a deterministic Schrödinger equation. And the next step is, well, don't just take this coherent term here, but look at the physics of fluctuations, and that corresponds to the first term in the Lindblad equation. And we also simulated this physics, and I will not go into the details here, but what I will show you is that if you include fluctuations, that changes significantly the survival probabilities of your quarkonium. It changes the speed by which it melts, and it changes the speed by which different types of states melt. So what we showed is that these additional terms are really relevant if you want to get a accurate description of heavy quarkonium physics. And so even this one here is still missing the dissipative part, and I will skip this. And if you then include the dissipative part, then you have to simulate the full Lindblad equation, and you can do that using a so-called quantum, the method of quantum state diffusion, which allows you to describe or implement any Lindblad equation in the form of a stochastic nonlinear Schrödinger equation. So not a deterministic Schrödinger equation. It needs to be a stochastic Schrödinger equation, and it actually has to be a nonlinear Schrödinger equation. But this is a general result. If you can write your dynamics as a Lindblad equation, you can always simulate it by an ensemble of wave functions that evolve according to this stochastic nonlinear Schrödinger equation. And by making this connection, we were able to derive for the first time from QCD a nonlinear stochastic Schrödinger equation that previously had been phenomenologically proposed in a different form from some colleagues. And this implementation here actually we could show that this is actually a really genuine Lindblad implementation, which means it really maintains the positivity of the spectral of the density matrix that was previously not possible. And I showed you these two pictures last Friday as the outcome of the 1D evolution, where we could show that when you simulate the full Lindblad equation, you can actually thermalize your heavy quarkonium states to a universal steady state at late times, which actually exhibits a thermal distribution of states. And with apologies to being very fast on the last part here, I would like to conclude by hoping to have shown you that conceptual and technical progress in the description of in-medium heavy quarkonium has been made by theory. We are in the quest to extract the heavy quark potential from Lattice Qcd is ongoing. We now know how to define and extract the potential from Lattice Qcd using spectral functions, and we have done so in well-controlled environments in quenched QCD, and we see that the potential, the real part of the potential, shows a dependence on the temperature. In full QCD, the results are quite puzzling. We find, depending on what kind of ensembles we use, we find different behavior, and our latest results are really require us to dig deeper here. Then when you ask, once you have the potential from Lattice QCD, what to do with it? Well, then my argument is, yes, let's use it in a Lindblad equation for in-medium heavy quarkonium, which then allows you to simulate the fluctuation and dissipation effects of the medium onto the heavy quarkonium by use of the real and imaginary part of that potential. And I told you, well, there's a lot to do. We need to improve the extraction of the imaginary part from dynamical Lattice QCD. And we, of course, need to extend our proof of principle 1D computation to 3 dimensions, include color structure, and then embed this into a realistic temperature background. And with that, I thank you for your attention.
Thank you.
And with some, before we go into questions, some shameless self-promotion, let me flip to this slide that there is a conference coming up at the University of Stavanger, the 14th Confinement Conference. It will be an in-person event this time. We will make sure that our venues are COVID safe. There will be a mask mandate, so you don't have to worry about meeting up with other humans after 2 years of Corona. And and even if you cannot come, we will be streaming the plenary session directly to YouTube, so you can enjoy some of the talks even remotely.
Fantastic, that's awesome. So so Alexander, sort of along the lines of that shameless self-promotion,
yes.
So would you then, I guess, encourage students and colleagues at the University of Cape Town to submit abstracts?
Oh, sure, yes. So abstract submission is open due to us trying to really provide the safest possible venue. There is, we have not yet opened registration, but that will surely follow, I think, next week. Yeah, we're looking very much forward to it. It's a conference broadly defined with interest in QCD. So you will find that there is, from confinement physics to deconfinement physics, neutron stars, beyond the standard model physics, to statistical methods and data analysis. There's something for everyone.
Wonderful. That's very, very good. Very, very good at it. Okay, so that was a great talk. Thank you.
Thanks.
I learned quite a bit. I have many questions, but maybe let's see if there are further questions from the floor first.
Yes.
Daniel.
Yes, Daniel. Okay.
It's just a question about sort of the end of the first topic you were talking about, where you showed the actual sort of extraction on real QCD data. And you said that it wasn't quite what you expected. I think 2 slides forward.
Yes, this one here. Yes, indeed.
I'm just unsure, what was it that you were expecting?
Yes. So if you think about static sources, static charges embedded in a thermal medium of light charge carriers, then from an analogy with abelian theory, so plasma, essentially plasma physics, tells you that if you look at the electric field strength generated by these between the charge and anti-charge, you would usually expect a Coulomb behavior if there's no medium. But then if you have color charge, if you have electric charges floating around in a plasma, then they will screen the static charges, and that will weaken the electric field between them, and will do so in an exponential fashion, and that is what is called the bi-screening. And so the fact that in quenched QCD, and of course what my intuition says has nothing to say about the world out there, but I saw the behavior in quenched QCD where you see that below the deconfinement transition you have a linearly rising potential, and then as you go into the deconfined phase, it appears at least that the data points indicate that this potential eventually flattens out, and this would be an indication of the presence of the bi-screening. And why that would be different in full QCD, that is very puzzling to me.
Okay, yeah, I can see. I can imagine on that graph there is no flattening out on any of the data sets. So
there's nothing here, and so since what I expected to come out doesn't matter, as a scientist I have to accept the empirical reality. However, what I need to make sure is that there are no systematic effects in here that account for this difference between the quenched QCD result and the full QCD result. And one of the things, for example, is that we are now using a different method here than we used for quenched QCD, because the underlying data does not obey the constraint that all the spectral features are positive definite. And that is a major difference here.
Okay, yeah. All right, thank you.
Sure. Blessed, I saw you also.
All right, thank you for the nice talk, Alexander. You probably touched on this during the talk, but I got lost at some point in terms of what we really learn about the in-medium properties of quarkonium through these spectral functions. And also at some point you spoke about the difficulties in extrapolating to the continuum limit. And I'm wondering if there are any experimental observables that we can draw parallels to these spectral functions, that can help us understand what's happening there a bit better.
Okay, thank you very much. This is a very important question. Namely, first of all, why are we doing all of this? So there's 2 ways that you could answer this question. If you have the potential, you can do 2 things. You can either use it to, so what I want to do with it is, once I know the potential, I want to understand what kind of real-time evolution of the quarkonium follows from it. And then I want to compare the outcome of this real-time evolution with what is measured in experiment. So the end goal will be to say, we have an idea of the temperature distribution in a heavy ion collision. We have an idea of the distribution of heavy quark antiquark pairs being created in the early stages. And now I evolve them according to the information given to me by the in-medium potential. And that tells me from the initially produced epsilon1 as only so few survive at the end of the collision. And then I can compare this with the measured yields for the, say, a bottomonium 1s state. And so what I would like this research to allow us to do is to understand and explain the distribution, the yields of epsilon and possibly charmonium, quarkonium states that are measured in experiment. That I would like to answer to your first part of the question, and the second part of the question is the taking the continuum limit. So, for example, you can, when you look at the Wilson, when you do lattice QCD simulations, lattice QCD for quantum field theory, it provides a regularization of your quantum field theory, and as you take the continuum limit, you're removing that discretization. And to define a quantum field theory, you first have to write down the path integral, you have to regularize the path integral, and then you have to renormalize it to be able to correctly make sense out of it. And this is where you have to then in lattice QCD spend work, which is taking the continuum limit naively would mean that you run into the apparent singularities of quantum field theory that are not really singularities, because they simply mean that we have not yet carried out renormalization. And for the Wilson line correlators that we look at, the renormalization effect means that as you make the lattice spacing smaller and smaller, so you go towards the continuum limit, the correlation function, let me show you. Yes. So for example, here, if you take this correlation function, as you make the lattice spacing smaller, what you would find is that the values become systematically smaller and smaller, and so it becomes harder and harder to simulate these correlation functions, the Wilson line correlators, closer to the continuum limit with the same signal to noise ratio. But you can understand this shift, and renormalizing means to undo this shift, and then you can make a well-defined continuum limit of these correlators. So in principle, and actually also in practice, you can take the continuum limit here.
All right, thank you. I just have another quick follow-up question
Sure.
on my first question. I know that there are quantities, just like quantities that describe collective behavior, such as the V2, for example, that we have no theoretical means, and I think experimental means of describing the real-time evolution of such quantities. And you mentioned now that with these spectral functions that we can actually build a sense of real-time behavior of Qualconium. Can that be used sort of to understand collective behavior in medium?
Unfortunately, the spectral functions that I now refer to are only one small piece in a chain of theoretical ingredients that would allow you to, in the end, describe the V2 of Quarkonium. So the spectral functions I discussed here allow you to extract this potential, and then you would use the potential you extract from the spectral functions in a real-time Lindblad equation. And that Lindblad equation, if it is formulated with realistic enough approximations, then this should allow you to also compute the V2 of the heavy quarkonium. So unfortunately, the spectral functions I've been presenting to you here, you cannot directly read off, so to say, the phenomenologically relevant properties of quarkonium directly from these spectral functions.
Okay, all right, thank you.
Sure.
Okay, super. Lawanda, you had your hand raised for a little while, but I think you took your hand down.
Well, it's a simple question there. What's this quenched QCD versus real QCD? I think I missed that. What's the difference in those potentials?
Yes. So the point essentially is that we have become very, very good at understanding probabilities, but we are still technically very, so to say, in kindergarten when it comes to handling quantum complex amplitudes. So that is, while classical physics you can describe mostly with probabilities, quantum physics requires amplitudes. And so the current state-of-the-art methods to evaluate the path integral rely on a probability interpretation of that path integral, meaning you want to write your path integral in purely real objects, because then you could say, oh, computing this here looks like I am computing as you would say, an expectation value over a probability distribution, e to the minus s. And if you were to write down the original real-time path integral, it would not be e to the minus s, but it would actually read e to the I times s. And one has to be honest to say nobody knows yet, or nobody has yet a robust way how to compute the Feynman path integral in Minkowski time directly, non-perturbatively from first principles. So the moment you have an e to the is here, all bets are off. All the established methods for sampling or stochastically evaluating your path integral do not apply anymore. And there's a large research community that is actually working on trying to make sense out of how to simulate this real-time path integral. And you might have stumbled upon headline or keywords that is called complex Langevin or Lefschetz thimbles. If you hear these terms, that is the community that is really trying to make sense out of how to formulate and simulate the path integral directly in real time. And so far, one has only achieved this in essentially very simple model systems.
Yeah, does that answer what you mean by quenched versus
sorry, yeah, that was lingo. That was you correctly call me out. I did not specify what quenched is. Thank you. So actually, quenched simply, so full QCD means it's a theory of interacting quarks and gluons, and quarks, due again to some technical reason, are much more complicated to simulate than gluons in the path integral. And when I say quenched, what I mean is that I'm looking at a theory that where there's only gluons present, but no light quarks. So this is a approximation to full QCD with no dynamically created or destroyed U and D quarks. And this is usually used as a let's say it's a cheap way to get a first hint at what the physics of full QCD could be. And then if you want to get a precision answer to your physics question, then you actually have to go and simulate full dynamical QCD where the light quarks are also included dynamically.
Oh, okay. Thank you. Just one more thing there.
Sure.
So with your results, your surprising results with the real part of the potential not changing.
Yes.
With temperature, what's the physical interpretation of that? Is it there's no confinement or deconfinement that you see, or?
So the thing is, this is what we got out. We published it to show this is what we get out. I have been very adamant while writing this paper with my colleagues is that we do not assign a physics interpretation to this yet, because I don't think we have. I believe so. For example, it has been established that the biscreening exists in QCD non-perturbatively. So people have been investigating the so-called color, the color singlet free energies, which is a thermodynamic quantity that you can relate to this screening radius or the screening mass, and they all hint at the fact that actually the biscreening is present in QCD. And why the biscreening, for which we have very good reasons that it exists, and we have a lot of indications both analytically and numerically that it exists, why that should not manifest itself in the real part of this static potential is I would not be able to understand. But I think it's good scientific practice to say, okay, this is the results, this is the methods we used, this is the results we got. We find it puzzling and we need to better understand what's going on. But we should still say that is what we got with the methods we have. So I would like to refrain from attaching a physics interpretation from that result as of yet, and wanted to simply show you that this is still a field in progress, and that there is, as you improve the methods in one direction, there might be these competing interests with other types of analyses. So these improved actions can help you for the thermodynamic properties, but they might be interfering with our ability to do meaningful spectral reconstructions on the other hand.
Okay, thank you.
Okay, super. So very, very quickly, let me
Thanks.
once again.
Yeah, thanks for the questions so far.
Yeah, no, super. And I have to go. I have another meeting that has already started. But I think, Alexander, I'll shoot you an email with some of the questions, and that's great. And I encourage anybody else to do the same. Let me stop recording and thank you once again.